Okay, so here's our next example. It's a device reliability example. Again, we know it's an exponential or log function because we've got a variable in the exponent, so it's an exponential function. And so it talks about in engineering, and especially in industrial engineering, this is used a lot. Reliability is often defined to be the probability that a device functions for a specified period of time. In this context, the reliability of a certain mechanical device is described by the function R of t is e to the negative t to the t over 1250, and that's raised to the 1.7 power, where R denotes the probability the device functions for at least t hours. So I've already done some of the setup down here. I've written our equation. We've defined that R of t is the probability the device functions. So that's not going to have units. We know it's going to be a number between 0 and 1. 1 meaning that we're 100% certain that it's going to function. Down to 0 means we're certain it's going to fail. T being after that many hours. So we would hope that at time 0 we get that it's completely reliable. If it falls apart just sitting there, then we have a problem. But as time goes on, it's going to get lower. So just from a quick sketch, we would, and again, this isn't thinking about things, but just thinking about what should happen, we should see something that kind of, so it's at 1 here, and then as it goes, it's going to kind of level off. And it should never actually hit 0 where we know it's going to fail, but it's going to get really close to 0 as we keep going throughout time. All right, so the questions are actually asking. So what is the independent and dependent variable? So again, they ask this almost every time. If we have R of t, that one's independent, that one's dependent. So our independent is t, which is measured in hours. R is our reliability, which is just a number. Again, and it's going to be a number between 0 and 1 at any time. So if we get a number that's not that in calculating our reliability, that's a good indicator that we made some sort of error. So part A, easy to answer. Part B, fairly simple. It wants to know what is the probability, so what's R, when the device functions for at least 1,500 hours. So it gives us this time. So again, that's just asking R of 1,500. So that's e to the negative. And this is where being very careful to write neatly will help, and not my strong suit, as you know. So it's negative that raised to the 1.7. And so this is going to be a little bit tricky to put in our calculators. Probably a good idea to kind of break it down. But I'm going to try to do it as one big thing. And we'll see if it looks right. So that's one of the great things about these graphing calculators is they have the display to show you what you put in and see if it looks right. So I'm going to use my e to the x function, so I have to hit second, e to the x. I want it to be negative. Then I have to do the part that's in parentheses, 1,500 divided by 1,250. And then that I still have to raise to the 1.7. And then I have to close parentheses because that whole part is the exponent. So, of course, calculator knows that it's going to do this part of the exponent first. Well, it's going to do the part in parentheses, and among the part that's in parentheses, it's going to do the power first, and then it's going to do the part within this parentheses. So we'll do the division, we'll raise it to the power, we'll make it negative, and then we'll put it in there. And so I get that it's 0.2558, and I'm going to write that on there completely. Again, probably a good idea on this might be to break it down part by part. That this is the same as e to the negative, what's 1,500 divided by 1,250 is 1.2 to the 1.7, which is the same as e to the negative 1.2 raised to the 1.7 is e to the negative 1.3633. And again, that's just grabbing numbers in my calculator, so I want to make sure to keep all those numbers in my calculator so I'm as accurate as possible. And then I could take e to the negative, and I like to use the answer function so like precise. And I get the same number of 255.082. So the probability that it survives for 1,500 hours is 0.2582, or as you might think of that, that would be one way to say it. Another way you might say that is 25.6%. And probably 3 significant figures would be sufficient on this one, although they did go all the way out to 4 significant figures on both those parts. So maybe I should, so that one has 4 significant figures. This one has 3. I would say this would likely be acceptable. 3 significant figures is generally acceptable in most engineering practice unless there's something else there. But yeah, so about 1 in 4 devices are still going to be working after 1,500 hours. That's maybe good, maybe not, I guess, depending on how often you're planning to use it. So part C asked, and we're used to this kind of happening, is what time corresponds to the device reliability. So it wants to know T equals, I'm trying to figure out T when R is equal to 90%. And so the first thing you have to realize is that means that R of T is 90%, which is the same as 0.90 when I write it as a decimal. And so again, hopefully you can make that correlation pretty quickly in your head, just like I kind of skipped over how to do that. Obviously it's a decimal, moving the decimal point 2 places to make it a percent. Same sort of thing here, move the decimal point 2 places, makes it a decimal instead of the corresponding percent. So that means that 0.90 has to equal e to the negative t over 1250 raised to the 1.7. Okay. So the good news here is that I'm already using e, so I know I want to use natural log on both sides. We talked about using, if we want to get things out of exponent, we need to use log. Sometimes we may use log base 10. Other times we like to use natural log, or it's more common to use natural log. If we have e, we're going to use natural log because natural log is log base e. So the natural log of e to the negative t over 1250, and that part is raised to the 1.7. So the natural log is 0.90. Log base e of that is just that, so it's negative t over 1250 raised to the 1.7. Okay, so now we've got t out of the exponent, but we still have a complicated thing to answer. Because we still have this, we still have an exponent in our equation. It's not a variable anymore up there. We just have a power question, not an exponential question. So the next thing we want to do is we got to get the negative to the other side, because again, we're trying to solve for t. So we're going to make this negative natural log of 0.90 is going to be t over 1250 raised to the 1.7. And again, we talked about if we have a variable up there and want to get it down front, we can take the natural log. But if we try to take the natural log of this to get the exponent down front, that would work, except then we have t bound up in a natural log. We don't want to do that. So the way we get rid of numbers in the exponent is to raise it to the inverse of that power. So in other words, we would take both sides, the negative natural log of 0.90, and we're going to raise that to the 1 over 1.7 power. And of course, if we take this side, t over 1250 raised to the 1.7, and raise it to the 1 over 1.7, well then these are going to just cancel out and these are going to multiply together and become 1. So this is the same as t over 1250. And then all I would need to do to solve for t then is I just have t over 1250. I can multiply both sides by that. And so I get that 1250 times negative the natural log of 0.90 to the 1 over 1.7 power is going to equal t. And again, if you're brave, you can put this all in your calculator at once. It's going to look something like 1250 to the negative natural log 0.90, that whole thing raised to, I'm going to have to put my exponent in parentheses, 1 divided by 1.7. So again, we'll see what we've got here. So 1250, I'm going to put a time sign in there just to be safe, because sometimes it gets so I'm going to insert a time symbol. Negative natural log. And so does that look like the thing we were trying to get? 1250 times the negative natural log of 0.9 raised to 1. So that looks like it's right. That t equals 332.67. I'll move it up here so maybe you can see it. 332.67. And again, it looks like we had all right. And so that's good. Again, you could probably a good idea to maybe break that down a little bit. You could do things like 1250. If I just did the natural log of 0.90, I get negative 0.105361, so I can make that negative becomes a positive, so I know this part in here is 0.105361, but I don't want to round that as much as possible, and that this part is 1 divided by 1.7. This part is 0.588. If I want to do some simplification. But again, the best way to do that is make the calculator do all the rounding. So I can do, and then I could take that number. But again, since I want to make my calculator to do it, I'm going to say let's take the answer from a little bit ago, raise it to the last answer. .266, multiply that by the 1250, and I get back to the same answer, 32.671, but lots of details in there. Okay, so this my original information was all had 4 significant figures, so I'm going to put 4 significant final answer. I'm going to write it more neatly that t is 332.7, and what's wrong with that? I haven't put units on it. What was t measured in? It was measured in hours. So what that tells me is that at 332.7 hours, I would still expect 90% of the devices to still be working. Again, if we wanted to draw a quick sketch of this, just to kind of think about what it would look like. This is time in hours. This is reliability. I know at time 0, it has to be 1. And what really ends up happening with this, because we've got this strange situation of a power in the exponent, is it kind of starts off a little bit level for a second, then it droops down, but then eventually, as we get out to longer and longer times, since we have e raised to the negative power, that remember negative powers basically are making us have fractions, that we're getting bigger and bigger, 1 over a bigger and bigger number, we're getting closer and closer to 0 until we're virtually at 0 on that.